And the second one is if there are simplified model for simulating dynamic behavior of still Joyce Gordon structures. Okay, and then that one, I already explained that. And then this one is also a very interesting part of that because we need to take up the fixity of the column base. So there's a pin and the fix, there's an ideal case. I want to take up the in between, the partially restrained case. What kind of design criteria should be considered for site design of these structures? So that's the main questions for this research. And then I just explained this one very quickly because that one is the design part of that. So there's an actual model, and then there's an ASC7 for the applied load, and then site design of the United States use the International Building Code, IBC, International Building Code. And then, so this one is at the applied loading, and the border depth is at the 40 inches, and then joist space is 5 feet. And then one of the important things that I will take up for the analysis part of that in the later, but design part of that for the conservative design, just assume the pin support. Okay, so that is the one I will talk about later. And then there's just 3 locations for the Los Angeles and Boston and the Salt Lake City, and there's different kind of member size, and then Joyce brothers, and then column, and then top chord and bottom chord using the angle sections, and the column use the wide fringe shapes. And then this number is a little bit interesting because the Still Joyce Institute have some own catalog. That one is that their own code numbers. So maybe you can check from that one. So, but the main thing is that there's a wide fringe shape, and then there's a bottom and top chord is the angle, double angle shapes. Okay, double angles. And then I just want to actual design for this connection part. Especially connection is important part of that. I just want to make a rigid connection and then transfer all the moment, and then this part hopefully have some yielding mechanism part of it. And then so there's a design. There's some top chord, and then there's a top plate, and then there's a plate, and there's column members, and then you can see that there's an actual my test specimen. Okay. So I just keep that clear. And there's a bottom chord. So bottom part of that, and then there's stabilize the plate and the welding. So weld the problem. And then there's welding, and then there's the actual one, and then you can see the strain gauge, the rosette to measure the strength to the steel members. And then there's a column base details, and then there's actual one, right? So column base details, there's a at the time, my doctoral study is okay, but now this is not allowed because for the safety of the buildings, only 2 anchor bolts, that's not enough. At least should be more than 4. Okay, in that case, my research is more valuable because the column fixed effect is more. This one, even though. So that one, I just want to mention about that. And then before the test, I also using some push-up analysis into the frame, and then I just want to show that part is the press hinge formation. So I just want to verify that what is the amount of force to make some press hinge part of that, and then get some push-up analysis result, and then that is the sway and the deflection, and that is the base shear part of that. So around the 33 kips, there's a first hinge formation, and then around the 40 kips, there's a second hinge form. Okay. And then full scale cyclic test. That one is that this is a reaction frame, so that is not the specimen, and with the actuator, and this is the actual specimen. Okay, so that one is the actual specimen, and then I just show you, and this is the actual specimen part of it. So I build this frames, all frames, and hang this kind of concrete girder. Okay, and then first time just people look at this one and they think, oh, this is a concrete test, but this is not a concrete test. This is actual frame for the frame. This one is for the only take of the what? There's a gravity load part of that. Gravity load part of that. And then that is a reaction frame and the actuator. So we can apply the cyclic loading, right? This one. And then that is definitely you need to measure all the strain and the deformation. So you can put the potentiometer and then strain gauges and then LVDT for the displacement at the column base part of that, because we want to know about the fixity of the column base. So that is so around maybe 120 strain gauges applied to this displacement. Okay, and then the lateral load history, apply this load part of it. There's a percent value, there's a story drift, and then how can we determine that one? Very easy part, there's a height and there's a sway, so there's a delta over h, and then times 100, you get the drift angle. So we just this amount, 0.5 and 1%, something like that. Okay. And then there's a full-scale cyclic load, and then I just want to, in the test result, test it, and then with the white paint, you can see there's some formation of the plastic hinges. So there is this is a bottom coat. So this under the bottom coat, there's actually yielding heavy. So that is a good result of this test. And then there's a very interesting graph. You can see that there's a x-axis is the top drift, y-axis is the lateral force, right? And then this is a cyclic loading, and then that one is the behavior, and then that is 0.375, 0.5, 0.75, and the different color. There's the actual test data. But these two line is very important one. That is assume the pin. That is assume the partial release. That is the actual behavior. This one. And then we can also observe the column base uplift. And then you can see that not the other side, but this one is the LVDT, measure the dimensions. Okay, and that is 3% drift level. We can observe the column lift up. And then definitely you want to know that the rotation and moment measurement for the column base, because I want to put some partial release column base condition. And then for the angle part of that, we just measure different displacement value from the LVDT, and you can find the angle, right? And then in the column part of that, strain gauge values, and you can also find the moment values. Just assumption is just a linear distribution, okay? And then, so I actually got this kind of result. Okay, so it's a good one, and we can actually find the stiffness of the column base. So dynamic analysis part of that, using some 2D modeling and the SAP 2000. So there's a push-up analysis. I just showed that one in the push-up analysis before. And then there's also 3D modeling using Abacus. So Abacus is a very good software. So I also, but it takes a lot of time for the modeling and all that part. The main reason I want to do that is that the compare result of this 2D one during the SAP 2000, then very complex model, 3D modeling for the Abacus. And then, actually this is the frame capacity, and the SAP 2000 and the Abacus, there is not much difference. So actually, in the practical way, you want to save a time, 2D model is also a good solution for that kind of thing. But that one is I'm going to show that. And then, the hysteric behavior, linear one, but you put some nonlinear part of that, you can have some nonlinear behavior over there. And then effect of column-based fixity. I also, in the literature review, there's a very interesting method. There's a compound method. You analytically find without that kind of test, actually estimate column-based fixity. So there's each component, find all the stiffness of each component, and the second step is the assembly. That's it. So there's a simple procedure, and then there's a very good result, because that one is the full-scale test result. So actually, you know the LVDT and strain gauge, I can find the rotation stiffness part of that and moment capacity. Compound method, there's maybe around 5% difference. So there's a good method in the compound method is that because if you don't want to some experimental work. Maybe comfort method is one of good way to derive the column-based fixity. And then I'm just using some bilinear model because we have a test result for the moment rotation curve. So there's a bilinear model. So there's a bilinear model. So I want to apply that bilinear model of the column-based fixity in the actual analysis part of that. And then there is a very interesting result. You can see it also same. So this kind of graph, all this part, that's the actual test result, right? And then this one is you assume that the base pin, okay? This one is you assume that fixed, okay? So PR is in between, right? And this one is actually bilinear model, and this one is the linear model. Linear model means that just one slope, right? Bilinear model is two slopes, right? So actually bilinear model is a very good result compared with the test result. And then conclusion part of that from the design result, the same member size can be used for Los Angeles and Salt Lake City, but heavier members are required for Boston area because there is a heavy snow load. The push-up analysis indicates the desired collapse mechanism. And then weak column, strong beam, you can use this one for the single story building, okay? But the typical way you should design for the strong column, weak beam, okay? You just know that this one for this presentation only, but don't memorize all the things because usually you need to pursue for the strong column weak beam. Okay, I just some different thinking and find some solution for this kind of spiral type of structure. And then the stiffness of the test frame was around 11 kips per inch, and the value shows that the assumption of a pin base underestimate the lateral stiffness. And then the columns began to fail in a flexural torsional mode shortly after reaching the press capacity after 3% drip level. It means that there is a ductile behavior, ductile failure of the building. And then you can put I just did not expect too much, but you also add some model loop deck and the bracing members. That is also different kind of dynamic behaviors. I did not mention too much about that, but column-based model, comfort model is a good agreement with the test results. And then time series result shows that the loop drift is decreased, and then base shear is increased by constant column-based fixity. So that's the main conclusion part of that. But the actually seismic coefficient is an important part of that. So this type of the buildings, maybe ordinary steel moment frame. Think about that, and the height limit is the single story, and then height is the maximum 60 feet. So this model building type is okay for use that one. And then decide some R value. So I still need to more work on that to find the appropriate R value for this system. So you heard of the R value, right? What is the main purpose for the R value? You need to take care of the ductility of the building. For example, eccentrically braced steel structure, there's maybe around 8 is the R values. But the actually masonry building, unreinforced masonry building, something like that, R value is at the 1.5, right? So that is related to the ductility of the building systems. Okay. And then this is maybe you can download this material, and then this one is a very useful one. There's a quantification of the building sizing performance factors. That with PIMA P695 is a very good reference, and you can use for more part of that. So this, I just based on that, I just want to do the more future research based on this report. So there's what I want to talk here. Okay, so I give us some other thing, but any questions? So there's a global thank you part of that. Okay.
Is there a Vietnamese thank you here?
No.
No? Oh, really? Oh, okay. Please let me know. I just added that part of it. Important thing.
How about Iranian?
No.
Oh, really? Oh. Okay. Okay. Okay, so any questions?
Yeah. Okay. Thank you very much. Yeah.
And then
We have any
I
questions?
just want a couple of pictures. Maybe can I show the couple of pictures to them?
Yeah, sure. Yeah.
So I want to show a couple of pictures. Okay.
원래가 그렇게 아니었는데 요새 갑자기
Actually, in the United States, I also bring the student to the field, so there's a field trip. And then one of the popular system for the condominium, the residential buildings, even though 5-story, or maybe more than 5-story, is also in the side area using the actual wood material, timber material. So there's a very impressive part of that. So there's a 5-story building using some timber materials, and then I want to share with you that is condominium. Yeah, so that one, so you can see the picture of that timber structure. So, wow, so in the California using some timber material in this one. So they usually like some timber material. And then in this part of it, there's a wood seismic shear wall. This part of that. But anyway, in the actually lower story part of it, it's a little bit difficult. Only using the timber materials, and then so that's then there's a picture, but you can see that that's used some steel materials, the combination part of that. But the main thing I want to show you is that in this part I also steel, right? You can part of that. But maybe you saw about that one. This is called what? There's a dog bone, like a dog bone type of thing. So why you make this kind of thing? You want to make a beam collapse first. So that is one of the examples. So my research topic is the opposite, but to make sure that there's like a fuse for some electric circuit part of that. So eventually, big expected earthquake, no matter building collapse, right? We design it, but we cannot make a very super strong, somehow magnitude 9 or something like that. No matter we cannot avoid the collapse of building. Okay, what is the actual preferable mechanism? There's a maker. This one is that all the deformation over here and the collapse that beam force, not beam force, not the column. So there's a strong column with it. So that's the reason I want to show you, because as a student, there's the most important concept you need to understand that. Okay, so that is the main thing I want to show you. And then now, any questions?
Can I have a question?
Yeah, no problem.